In chapter 4, we're going to be looking at the current atomic model. And in this section, we're going to look at how they got to where they are now. So we're going to start off talking about a couple other things. So microwaving pizza, or a better option for what to do with Peeps, the little marshmallow creatures that we see around Easter. And we'll get to that later. So one thing to think about, when you microwave pizza, and microwaves are a little bit better now than they used to be, but especially if you don't have a rotating pan or something in your microwave, why doesn't it always cook evenly? Sometimes you have hot spots and sometimes you have cold spots. And, not necessarily just pizza, but depending on how old your microwave is, if it's older, you might get this with lots of different types of food. So that's something to think about that we're going to answer throughout this chapter. So we are going to be looking at waves. So the first thing I want you to think about, what do you know about waves? So whether we're talking about ocean waves, whether we're talking about waves in science, what are some of those common themes with waves? So you can see here, we've got water waves, and they're going up and down. But if you were on the beach, maybe they're coming in and out. So if we look at a wave that's going up and down, we can see here, this is called a transverse wave. And we're looking at a wavelength. So a wavelength you can think of as the one top point to the next top point, or one bottom to the next bottom. So one complete wave cycle. So wavelength is going to be corresponding points on adjacent waves. So what does that really mean? So let's say we pick this point here to start with. If we completed one complete wave cycle, we would have to go all the way down, all the way up, and back to that midpoint to complete one wave cycle or one wavelength. And we could pick a different spot. We could pick what's called the crest. So one crest, go all the way down, and then all the way back up to that same point. That would be one wavelength. And so a wavelength is a distance, so we would measure from the one point to where we began the cycle to the other point where we ended. The symbol for this is what looks like an upside down Y. It's called lambda. It's a Greek letter. And so wavelengths are measured in distances, whether that's a meter or a centimeter. Maybe it's a small wave, so it's a nanometer. So again, we're looking at those metric prefixes when we're talking about wavelengths. Frequency is going to be like a speed or a velocity. So how fast is that wave moving? Or how many waves are going to pass a point in a certain amount of time? So if we look at these two examples here, if I were to draw a line and I said in 30 seconds, how many waves would pass that line in 30 seconds? Well, the top row, we're going to have more waves pass that line in the same amount of time as opposed to the bottom example. So this top row would have a higher frequency, but it has shorter wavelength. Again, at the bottom, we would have lower frequency, or less waves would pass that point, but they have a bigger wavelength. So the symbol for frequency is a V, like velocity or speed. This is going to be measured in waves per second. So how many waves pass a certain point in a time period, in the second. And another name for that is hertz, and you might have heard of the hertz before, dealing with sound or instrumentation or sound systems. If we look at these little guys here, I always find this rather soothing to watch, but each of these different shapes or colors are giving off a different wavelength. So if you look specifically at red, he has a large wavelength compared to the little blue guy he's completing what, 4 or 5 maybe waves per one of the red waves. So if we were to ask which shape or which color had the biggest wavelength, we would say the red has the biggest wavelength and then the blue has the smallest. But if we were looking at frequency, the little blue guy would have the largest frequency because he has the most waves per time period, and the red would have the smallest frequency. So wavelength and frequency are always going to be inverse of each other for a specific wave. So if the wavelength is large, the frequency will be small. So when we look at the equation using wavelength and frequency, C is the symbol for speed of light. And so if we multiply wavelength times frequency, we will get the speed of light. And the speed of light is a constant. It's always the same amount and it's never going to change. So when we are looking at the speed of blue light or the speed of red light, it will always be the same amount. And then we can use that to find either the wavelength or frequency depending on which one is unknown. So this might be a familiar image to some of you. Basically, it's a prism. So we have white light being shown through a prism. And so it's reflecting all of those different colors of the rainbow that make up white light. And so each color is going to be bent based on the wavelength. So we see down here, we get that indigo and violet end of the spectrum, versus at the top with larger wavelengths, we have the red and then orange, yellow, green, blue, violet. So just because of the different size of the wave, it's going to bend differently through a prism, and that's how rainbows are produced. We have a little chemistry cat here for you. So when we look at this slide, now these are not exact, but they're rounded, so they're pretty close. But red has a certain wavelength and a certain frequency. So if you were to multiply these two numbers together, you would get the speed of light. The same thing for each of these colors. Multiplying orange, wavelength times frequency, you should get the same speed of light number that you get for red. So I'm going to give you a minute, pause the video, get your calculator, and multiply each of these numbers together and see what you end up with. And they all should be, discounting rounding errors, about the same value. So when you've done that, these are the numbers that you should have gotten on your calculator. And again, because of rounding and we weren't using the exact frequency and exact wavelength, we've got about the same value though. So 300 million for each of these different values of speed of light for each color. So when we're using the speed of light to solve for wavelength or frequency, and if we go back, let's say we had 300 million as our speed of light, and I was given the wavelength, but I did not know the frequency, I would just divide. So that 300 million divided by the wavelength will give me the frequency. And the same thing if I'm given the frequency, but I'm looking for the wavelength, 300 million divided by frequency will give me wavelength. So this 300 million number is something that you should have memorized. When we look at what is called electromagnetic radiation, a lot of times people think of radiation as something that is harmful, and sometimes that is true, but it doesn't always have to be the case. Electromagnetic radiation is all the forms of light that are visible and non-visible. We typically think of light as, what we can see as far as something that comes from the sun or from, a light bulb, or different colors that might be emitted. But actually light would be any type of wave that might be emitted, such as X-rays or FM waves, things like that. So if we look at this spectrum. This includes all of the different types of waves. And so what we actually see, the visible light or the rainbow that we might think of, only makes up this small amount of the electromagnetic spectrum. But actually, it includes things like ultraviolet rays, X-rays, gamma rays. And then on the other end, we've got infrared, radar, FM, TV, shortwave, and AM. Here, you can see the wavelength. So something like AM would be 10 to the 4th meters, whereas FM would be 1 meter long for a wavelength. All the way down to gamma rays are going to be 10 to the negative 14th meters in the length of the wave. So when we're looking at the spectrum that we can see, the visible spectrum, the colors of light, we're looking at wavelengths in terms of nanometers. So when we look at the question that we discussed at the beginning, why do we get hot spots in our pizza when we cook it in a microwave? So a microwave is based on microwaves actually passing through your food, and they're going to vibrate the moisture that's in your food. So when we have a couple of different waves, like in this picture, that are coming together, so at a point maybe here, they're both touching the particles of the pizza at the same time. These two spots here might be where your pizza gets cooked, versus where the waves aren't coming together might be where your pizza gets cold. And so that's why if your pizza is rotating, this process works a little bit better than if it's just, stationary, not moving around.